My name is Barbara Ferreira. I'm the EGU Media and Communications Officer, and I would like to welcome you all to the 2012 General Assembly of the European We have organized 12 press conferences for you this week. Most of them, including this one, will have short presentations, and then I will open the floor for questions, both from the journalists here and those watching via web stream. I see that you've all received the summaries related to these press conferences. Other documents, digital copies of those documents and documents that arrive to me later will be uploaded to the documents section of the media website, so you can download them from there. This first press conference covers the general topic of geosciences and health, and we have Masatoshi Yamauchi, a senior scientist at the Swedish Institute of Space Physics, talking about radiation in Fukushima. Mark Lyles, Chair of Health and Security Studies at the US Naval War College, talking about dust exposure. And Rachel Lowe and Adrian Tompkins will be talking about climate and tropical diseases interactions. Rachel is a postdoctoral scientist at Catalan Institute of Climate Sciences, and Adrian is a research scientist at the Abdus Salam International Center for Theoretical Physics in Italy. And I will let you start now. Thank you.
Thank you very much. I am Yamauchi, and coming from the Swedish Institute of Space Physics. I'm a space scientist, so I'm not really the original scientist for this type of the work, but the methodology is exactly the same, and actually there is no scientific community existing to study the radioactive dust motion, because there is no such kind of data available. Chernobyl is the last biggest accident, but Chernobyl time that there is no good measurement network. And Fukushima is the first big nuclear accident with a very good measurement network. That means that we can really understand what, how the radioactive dust is moving in the air, and what is actually what kind of the health risk could be from such kind of data. So unfortunately, there is no such kind of scientific community because there was no data. So this is the first time that we can really understand the, how much the radioactive dust was on the air after the nuclear accident. And then the measurement method, the first slide shows that there are three types of the measurement methods. The one is, of course, the directly sample the dust, that's right number two. But and also one is also detecting the gamma ray, that is how strong the radiation from these things. And then those are the quite many people already know on the web, over the website and the broadcast, that how much dose rate people are talking about it, and how much dust is all sampled, something like that. But also that as a geoscientist, that we can also understand the motion from not such kind of direct measurement, but also indirect measurement, because the radiation makes that the atmospheric molecules ionize, because atmosphere is a very good resistor, and it ionizes, and this ionization makes that something that atmosphere has a strong electric field, and then this electric field change. You know that the thunderstorm, and from the time of the Franklin, that the atmosphere has a lot of electric field, and this understanding the electric field gives us the understanding the atmospheric ion. And this atmospheric ion is directly related to the radioactive dust, because you see, the radiation we call that ionizing radiation. That's why we call it. So the second graph is that here. This is the example of how the atmospheric electric field reacts after the contamination. So the accident, okay, there's earthquake, 11th of March, and then this is the location of this measurement is something 150 kilometers away from the nuclear power plant. It's quite long distance, and even this distance, you can see that the the daily, it is a 1 month data, and then you can see that the data is from about 60 volt per meter to nearly 0 volt per meter. So it is quite changed. And such kind of this electric field measurement is a very, very classic method that even Chernobyl time they have measurement. And we can compare how the similarity and difference. Chernobyl time we have a Helsinki data, and then it is 1,000 kilometers away from the Chernobyl, and then suddenly drop. But the pattern of the drop is different. For the Fukushima's case, first drop in the 14th of March, but it recovered a little bit. Then this recovery is a very, very mysterious, because once it is dropped, means that the radioactive dust is settled down to the ground, and it radiating all the time. So then if it is really settled down, then this ion shouldn't, the ion density keep very, very high, so that it should be 0 all the time. But it recovered. It recovered, and also this settled down takes place without rain. That Chernobyl case, all such kind of drop takes place with the rain. So that means that what happened in the 150 kilometers away, quite long distance. Think about the natural border between the European countries. And we have a lot of nuclear power plants. And one of the power plants have an accident 150 kilometers away. Still that we have a big effect. We can see it. So then it is not a national problem. It is a more international problem. Then this increase really tells us that actually the radioactive dust is, once it is settled down, to float up, because the electric field measurement and radiation dose rate measurement is two independent measurements. That means that we can really tell us about how high the radioactive dust is distributed. So we have two different information. So then we can really see that how it is floating over the ground. And then finally, the rain settled down the radioactive dust to the ground on the 20th of March. Then risk decreased a little bit. So next. No. No. It doesn't work.
Let's do this.
Okay, thank you. And then what is happening? What is the difference between the Chernobyl case and the Fukushima's case? Chernobyl case, for the European people, that actually all the dust go very, very high altitude. It is an explosion, and then from the high altitude and rain drop make it. That means that it is hardly attached to the ground. But for the Fukushima's case, first it is a surface wind bringing it, so the radioactive dust is floating above the ground all the time, and then some wind coming. Sometimes it is a weather system that when it recovers the 14th of March, that the atmospheric electric field increased. Then that means that it blow away and the dust is expanded. Then the 20th of March, the dry deposition happened. But this dry deposition, actually, the wind is not that high altitude. So even it is a rain induced make the contamination, but this contamination is not hardly attached compared to the Chernobyl case. That means that after the back. Yes, after the after it rained drop the 20th of March, then we have some daily variation recovery, and then that is minor signature that I'm not talking here, but there, if we compare with the radiation dose rate and electric field signature more carefully, then we can really see that even after the rain contamination, wet contamination, still that we have a dust is floating again. So it is a resuspension. And then, okay, next slide. So that means that there are three types of the contamination pattern. That dry contamination, the dry deposit, and then also that wet deposit but very softly attached to the ground, and then wet deposit hardly attached to the ground like a Chernobyl. So then what in the Europe we have to worry about in the future case is that this kind of a soft contaminated deposit. And That is the thing that we understand from the Fukushima's data. Okay, last slide. Next. Yeah. So this is so we can really divide into three periods. One is the most dangerous period until the first rain. So after the accident to the first rain, that the dust is floating around the ground, over the ground, very, very high dense. Then afterwards, although it attaches to the ground, that still that quite a lot of resuspension happens. That is about 50 days, 40 days after the accident, we still have a risk of the internal loss. Then afterwards, we look at more carefully that all the data. Then after even 3 months after, there are a lot of minor plume coming from the nuclear power plant area, because nuclear power plant area is a most highly contaminated area, and that is floating into these are the resuspended to going out. So even 3 months after the accident, then the risk remains. That is what I'm going to talk about in tomorrow. Yeah. Okay. Thank you very much. It takes longer time.
Escape. That's fine.
Sorry.
I hope so.
Hey, Cinque. Okay.
Did you hit something?
Just F5.
That was already on there. Okay, ready?
You're right.
Should I begin? Captain Mark Lyles, United States Navy. Presently hold the Vice Admiral Joel T. Boone Chair for Health and Security Studies at the Naval War College. I want to talk to you today about medical geology in the Middle East, potential health risk from mineralized dust exposure that I and my colleagues from the U.S. EPA, U.S. Corps of Engineers, U.S. Geological Survey, different universities have been working on since 2003. I have to put a disclaimer, although I am an active duty military officer, my views and the views of my co-authors are not necessarily those that reflect official policy, position of the United States Naval War College, Department of the Navy, Department of Defense, or U.S. government. Amen. I want to show you a film here that pretty much says it all. This is from military.com. This film was taken at Al-Assad U.S. Marine Air Corps Base in Iraq in April, I believe, 2004 or 5. You're going to see a schmall here, which is a large dust storm that's coming in. It's about 1,800 meters high. It's coming at about 60 kilometers an hour. I'm trying to use my conversions here for everyone. What you're going to see here is in this base, as you can hear the sound, you can hear it coming, that how intense this particular dust storm is. But one of the other things that you'll see with this film is this exposure that you're going to experience. You hear them telling you to take shelter, to get out of the dust storm, park your vehicles, to hide, protect yourselves. And in true military fashion, no one's doing anything. What they're going to do is, if you are driving a vehicle, if you're laying in the dust on any given day, if you're outside on any given day, you will be exposed to dust intensities approaching these levels each and every day. So what you're going to see here is this driveway, if you will shortly disappear now that you're starting to see the buildings disappear as this moves forward at about 60 kilometers an hour. You'll see a light off to the left. I don't know if this thing works. Right here. And the Autolux camera will try to open up as much as it can to take in as much light as it can. This constitutes somewhere between 50,000 and 70,000 micrograms of particulate, of PM10 particulate, 10 micron particulate, per cubic meter, it's probably a couple orders of magnitude of all particulate. Higher than that, so you're talking probably in the millions of particles per cubic meter. And as you can see how this was pretty intense. I don't know about you, but I would think that that might present a potential acute and chronic health risk. This is what we do this for. This is for the coalition partners. This handsome young man right here is my brother, came in a year after I did. But this is why we do this research. Dust in the environment and dust and health risk are not new anywhere in the world, as was evident a couple of years ago when they had the huge dust storms in Sydney. You will note that the levels of the dust in Sydney approached 500 micrograms per cubic meter. The average daily reading I had during my experiments was between 800 and 900 micrograms per cubic meter. That was the average daily exposure, which is double what you saw in Sydney, that caused worldwide interest. Of course, we've had the dust from the World Trade Centers. We've had dust from everything from silicosis to black lung from coal. So dust and health effects are not uncommon. We also see dust from the Aral Sea. We see dust from the Gobi coming over into Korea and Japan causing problems. So this is not new. This could be just any day. This is from Dr. Kathy Cahill, a colleague at University of Alaska that I work with. But this is really what it looks like most of the time. So it's a tremendous amount of dust exposure. It contaminates everything. It gets everywhere. Why is this important? It's important because this dust is a mineralized dust. It contains bioaccessible metals and heavy metals. It harbors viruses, bacteria, and fungi. And there is a tremendously high amount of these particulates in the respirable range. The problem with that environment is it's not like this room, the environment in this room where we breathe through our nose and our sinuses are able to, pharynx are able to filter out a lot of the dust in this room. In that environment where it averages 120 to 138 degrees or higher with 3 to 10% relative humidity, UV is from the sun exposure is off the scale, people breathe through their mouth, and they breathe a lot through their mouth, usually 5 to 6 times what normal breathing would be in a sitting room. So at those temperatures, with 80 pounds of material you're carrying, you're really huffing and puffing. So there is no filtration as particles come in through your mouth and into your lungs. This is what happens when these particles get into the lungs. If the particles are just inert, there's so many of them that they can close off small bronchioles and cause problems with getting gaseous diffusion in various parts of your lungs. If you just look at simple sizes of different deserts in the world, you'll see that not all deserts are the same. That even in this situation, Kuwait and Iraq and even Afghanistan have some of the smallest mean particle sizes. If you look at just simple chemistry as calcium and silica ratios, you'll see that every place on Earth is different. It's not the same. So a desert is not a desert is not a desert. You'll see that these particles here are oblong shaped like footballs, and they contain pores in them. They're actually hollow. They have pores within them, and they're coated. This is because that this area once was a paleo lake, and when that lake dissolved down into the silts and clays, it carried all the minerals in which it had dissolved over millions of years into those clays and silts that are now being particleized in the dust. The dust is widespread. It sucks water out of the air. It's respirable, easily airborne. It's non-clumping. It's a biocarrier. So if you look at a given day, this was the 14th of June or 15th of June 2004, you'll see that 3,500 micrograms per cubic meter during a peak hours of between noon and 1 o'clock. In this room, there's probably 1 or less micrograms per cubic meter, so 3,500 times that amount. If you look at particle sizes starting at 120 microns going down to below 20 microns, and a red blood cell is 8 microns, you can see that as the particle size gets smaller, the amount of metals in the particle also gets larger, which is anti-intuitive, but it's due to the coating. In this case, strontium at 2,700 parts per million, barium at 460 parts per million, vanadium at 50 parts per million, aluminum at 7,500 parts per million. We had levels as high as 10,000 parts per million, or 1% by weight. We start looking at things like nickel, 560 parts per million, yttrium, manganese, chromium at 52 parts per million, as high as 75 to 100 parts per million, of which we don't know what percent of that is chromium-6. We also have lead at 138 parts per million. This is a tremendous amount of load when you consider how much that everyone is being exposed to on a daily basis. As the particle size gets smaller, the amount of carbonate of the coating gets larger, and that's where we believe the vast majority of these metals are contained in, is in the carbonate layer, which makes them readily accessible and dissolvable in the human system, whether the lungs or skin or elsewhere. To go into the biology very quickly, as in the sixth plague of Egypt, it shall become small boils, or small dust into the lands of Egypt, shall bring boils breaking upon forth, plains upon man, upon beasts, upon all the lands of Egypt. So having bacteria in the dust in this part of the world is not unusual. We looked at the fast growers. We did classic clinical analysis of what we found in the dust types. We found quite an array of dust particles. You can see the hemolytic nature, or the ability to break down blood in some of these organisms. What makes this unique is that this occurred at much faster rates than what we normally see. This just gives you an idea of some of the isolates we found. Neisseria meningitidis, we were the first ones, I think, to report Neisseria being associated with dust particles. All the ones in the dark bands are either alpha and or beta hemolytics, meaning they break down readily blood. We did classic analysis. We looked at fatty acid methylesterase as well as 16S rDNA analysis sequences. And what we found was quite a few of these organisms break down blood. They're hemolytic. We also found quite a few of them that were absolutely immune to our top-of-the-line antibiotics, in this case vancomycin, although they were quite sensitive to penicillin. And that makes it unique until you realize that penicillin doesn't grow in a desert. And so these organisms had never seen penicillin before. It's classic biology, it's classic microbiology. We should take a lesson from that. We look at antibiotic resistance, again, quite a few. We look at microbiology. Since you're only as good as the information in your database, it's not uncommon that all the databases we use could not give us an identity on many of these organisms. In fact, in many cases, we had to do DNA analysis, and then we had a good approximation of what we were exposed to, because these organisms have evolved in an area where people don't live. When you look at different size particles, you'll see that you have different ecologies based on the size. We thought this was unique and, again, anti-intuitive. The smaller the particle gets, the more biota we get, and the more differentiated biota we get. It makes sense that if you're going to be a virus or a pathogen and infect snakes, you don't want to get too high in the atmosphere. But if you want to infect camels and humans, you might want to get higher. And so that's part of the theory behind why we have different organisms or different ecologies with different size particles. We found a lot of organisms we could not identify, and as you know, the expense in trying to identify things that are unknown are very, very expensive. What makes this unique in deserts of the world is these particles are hollow. This was done by Dale Griffin at the U.S. Geological Survey using CyberGo DNA staining, in which he shows the presence of bacteria and viruses within the particle itself. This is what helps keep the particles from being sterilized by the sun and keeps these organisms from desiccating and thus viable. This is a NASA film that basically shows, and it's not going to run, basically shows that these organisms hide in the crevices of these particles, and that's how they are able to survive, whether they're coming off the sub-Sahara or the Gobi and being transported all over the world. We also found, again, quoting one of our colleagues, Dale Griffin, that the viruses, there are more viruses per weight in these particles than any other dust he's sampled in the world, and the largest percent of RNA viruses he's able to see, which is not good because RNA viruses like to mutate. We've got new evidence coming out that we see that the existence of possible diseases linked to dust transportation across the world. This makes this important in the transport of infectious diseases via dust. All these organisms are contained in the varnish, what they call the desert varnish, the crust on the surface of the desert. And when you walk on it, you run a truck on it or a tank on it, you crush that up, and it takes years to decades, if not longer, to repair that. So this is what it looks like if you just look at the crust, and when you crush that up, it becomes particles. When you go to Afghanistan, you find even smaller particles, some of which 50% by sample are less than 10 microns, 35% by sample are 2.5 microns or less. But they are different particles. They're not hollow, and the bacteria and other biota are on the outside of the particle. This all becomes important based when you start looking at the recent report by King and Robert Miller at the University of Vanderbilt, in which they described constrictive bronchiolitis in soldiers returning from Iraq and Afghanistan, which up to this time had not been reported or yet diagnosed. I still think that we're going to see more and more problems coming from this kind of exposure, and this is what this work's about. So it's ubiquitous, it carries pathogens, it's bacteria, fungi, as well as a variety of metals, and we're still looking at what are the acute and chronic potential health risks. So that's where I'll quit.
Because we don't have much time left.
Okay. Hello, I'm Rachel Lowe, and I'm going to talk to you about some work I've been doing with my colleague Anna Stewart towards investigating how climate information, along with other factors that impact the disease dengue fever, and can be used for prediction purposes within an early warning system for dengue epidemics, particularly in southern coastal Ecuador. So advance warning of these dengue epidemics could help target specific interventions to mitigate and control the disease, such as destruction of potential mosquito breeding containers and implementing education campaigns in order to protect the vulnerable populations from the mosquito bites, which is how the virus is transmitted. Just going to bring up the slides.
Is it this one here?
Is this one down here?
Okay. That is mine. This one?
I think it's that one. Yeah. It's all right. Okay. So, by using climate information, and we find that this information seems to have a significant impact, in part, on the transmission of these dengue diseases, and this provides a timely opportunity for the meteorological services to work closely with the Ministry of Health and public health decision makers to be able to prepare active mitigation and control strategies several months in advance. So dengue fever is on the rise in Ecuador and across the globe. It's estimated to be affecting around half the world's population currently, with 50 to 100 million people worldwide affected each year. And it's transmitted by the mosquito Aedes aegypti. The disease is a severe flu-like illness, including joint and muscle pains, and it's often described as break-bone fever. And cases have been increasing over the last decade in Ecuador, and this is worsened by the fact that there are 4 closely related viral serotypes circulating in the country at present. So the site where we've been doing the investigation is in south coastal Ecuador in a place called El Oro, which is marked on this map. So there's many complex and potential drivers of dengue fever. So human drivers include things such as population growth and urbanization. So many people living in substandard housing conditions, often living in very close proximity to the dengue mosquito, which thrives in environments with discarded tires and rubbish, which can collect water and produce ideal breeding sites for the mosquitoes. And the environment intervenes by the rainfall filling these containers, and temperature and humidity influences the mosquito biology and development. And some large-scale climate phenomena such as El Niño and La Niña impact the local climate in certain parts of the globe. And in the coastal area of Ecuador, on average, when we have a El Niño event, so an anomalous warming of the Pacific Ocean, we tend to see increased rainfall and temperature in the coastal region of Ecuador. So within a model, we try to investigate, along with non-climatic factors such as the circulating serotypes and mosquito abundance, how the local climate drivers of dengue, so rainfall and precipitation, and the El Niño Southern Oscillation, how they impact on dengue fever. And we find that they have a positive association. And using a statistical model we've developed, we find that, for example, several months ahead of a dengue epidemic that occurred in February 2010, our model would have predicted an 89% probability of dengue exceeding normal levels. So this, in practice, could have been used to help the authorities prepare mitigation and control strategies in advance. And if you'd like to know more about this work, we have a poster on this in the Climate and Infectious Disease Interactions poster session this evening, 5:30 till 7 in Zone Z. Thank you very much.
Okay, I should try and be brief. My name's Dr. Adrian Tompkins. I'm a research scientist at ICTP. I've actually spent the last 20 years developing the physics of clouds in both forecast models and climate models, which are actively used. What I want to talk to you about today is how I've used those mathematical techniques to develop a new model for malaria, which we wish to apply both to the task of forecasting on monthly timescales and also longer-term climate projection of malaria risk. This work is in the framework of 2 projects of which I am the PI at ICTP. The first is Queasy, the second is Healthy Futures on the top right. And in a nutshell, the concept is that we take, as you see on the top left, forecast information of rainfall and temperature. Or on the top right, we maybe take climate projections of weather. And we use these to drive models for malaria in order to provide information to decision makers. Malaria, as you know, is an extremely important disease, lots of consequences that are extremely important, and it has very strong climate drivers. So in the next 3 slides, I want to explain to you very briefly what those climate drivers are, and then how we use those to develop this new model, and what is actually new about this model. Okay. So the strapline of the research is that in order to achieve this goal, ICTP, we've developed a new dynamical malaria model that can be used on a regional scale at fine spatial resolutions. I will show you an example of this, that accounts for the first time surface hydrology in a realistic way, but also accounts for population. So it can be applied locally on a regional scale. And that also has the ability then to incorporate interventions and immunity. So before I start that, I have one slide to very briefly explain to you the actual climate drivers of malaria, for those that may not be familiar to. So on the right-hand side, we have an example of small and larger scale ponds. Without water, the mosquito cannot lay eggs and actually continue the breeding cycle. So the rainy seasons in Africa determine the malaria transmission seasons. However, temperature is also very important in many aspects of the disease cycle. So the water temperature determines the larvae progression rate, development cycle rate. It also determines the egg development rate, and it determines how fast the parasite goes through its own development cycle within the mosquito. The mosquitoes, when they are born, they are malaria-free. They need to make one bite to actually pick up the parasite from an infected person, and then a second bite several weeks later in order to pass on the disease to an uninfected person. So the warmer the temperature, the faster the disease cycles. So temperature and rainfall information can give us a clue about the intensity of the malaria transmission season and also the spatial variability. If it gets too hot, you have increased larvae and mosquito mortality. So as we see on the bottom left, we have a peak transmission at temperatures of around 25 to 30 degrees. So these are the main climate drivers of malaria. Okay. So what we've done is we've developed a new malaria model, a dynamical model. The cartoon on the bottom left emphasizes that we have a gridded model. So this is for East Africa. You can see Lake Victoria there in the middle in white. And so we're showing, for example, Rwanda, Tanzania, the region of Kenya. And you can see how this is showing parasite ratios. It's the proportion of the population carrying the parasite. And we can see how the season progresses. The top left compares the model to data on the top right. And so we can see, for example, if I could point with a cursor without it moving on. Will it move? No. We can see that the area of Uganda, for example, is a region of endemic malaria with high transmission, whereas Burundi, the areas in blue in the top left-hand side, are areas of low transmission because we're at high altitudes, we have cold temperatures. The other thing we should emphasize is that one of the confounding factors always when you're looking at diseases in these areas is the lack of data. So the data on the right-hand side is from sparse, should we say, field studies supplemented with a statistical model. So data is a confounding factor. What's new about this model? Two slides just to emphasize that. One, as I said, is surface hydrology. So on the bottom left, we have an animation of the rainfall in the region. And on the bottom right, what we're actually showing there is the fraction of each grid cell that's actually covered by small-scale ponds. Okay, so you can see that these animation is showing the ponds growing and then decaying as the water evaporates or infiltrates into the soil. So this is the first model of its kind to try and represent that small-scale surface hydrology. The other thing that's new about the model is that it takes into account population density on a small, fine spatial scale. So if you have more people, you have a dilution effect. You have fewer mosquitoes per person, so you have fewer bites per person, so you have a lower transmission cycle. Of course, it's a lot more complicated than that. That's just the main zero-order effect. But the model is the first of its kind to be able to incorporate that into this framework, which means we're in a position now to start accounting for migration and immunity in the model, because there is the human component of the disease transmission in the model. Okay. This means that we're now being able to, for the first time, starting to apply it to forecasting and climate projections. So I'm going to finish on this slide. What it shows in the top left, for example, is the year-to-year variability in the transmission. So the blue areas have very low transmission, because essentially they're malaria-free, they're very cold. The red areas show where there's very high variability from year to year, the epidemic areas. These epidemic areas are where we can start to think about making forecasts using the weather information from the European Centre based in Reading, ECMWF. On the lower panel, I show some examples of the top row of present-day malaria simulations using various climate models. And below is the corresponding end of the 21st century malaria transmission season. And so you can see, first of all, that the models are very different. There's a lot of variability between the climate models, but also in areas such as the Ethiopian highlands that the transmission increases. But this is just one aspect, the climate driver. So I'm going to finish there. I think that summarizes basically where we are at the moment. Thank you very much.
Thank you. Thank you very much for the excellent presentations. We have time for one or two quick questions, if anyone.
I'm Jonathan Tyrone with Bloomberg News. I'd like to address my question to Mr. Masatoshi Yamauchi. Okay. Do you expect to see or continue the dust modeling based on pollen movements around the Fukushima site? Along with that, based on your study, would it be a reasonable forecast to say radiation may increase in times of drought when the loose attachment is more susceptible to movement by winds and other climate factors?
Yes, actually, the Dr. Stoll has made a lot of simulation, and he's presenting on Friday on actually using the recent atmospheric model, and then how the movement would like. And then my point is that the simulation is one important tool, definitely. But the simulation, Japan spends something billions of money to make such kind of simulation modeling for such, but it didn't work. Because of the emergency situation, the simulation is always different from the measurement. That I really checked all the detail, all the simulation results, and there's always some difference because there's a dangerous area and not dangerous area. And that means such kind of focus on the real time, because for the health risk thing that we really have to real time protection. The work what I'm doing is that for the future case, what kind of measurement method we need it and how much we can really make a real time focus of the motion. And that one, that we have to really collaborate with the simulation, but simulation, if it is simulation like the Japanese government didn't issue it, they hide it. So because the simulation is really not the reality. It's a kind of ideal situation, and we have to go to the very, very detail of the motion. In that case, we really need a measurement. That is the point that what kind of data we can get from the measurement. That is my point.
Questions? Yes.
Liz Callagher from Environmental Research Web. I have a question for Adrian Tompkins, which is, can you talk a bit more about when and how people will actually be using your forecasts to prevent malaria transmission, and how much money is going into that?
Okay, so the work is actually, as I said, under the framework of a European Union FP7 project, QUIZI. So that's a €3.5 million project with 13 partners, half of which are based in Europe, half of which are based in Africa. Our main forecasting partners are the European Centre for Medium-Range Weather Forecasts. In fact, my colleague from the centre is sitting here in front of you. The project has a time frame to finish in the middle of next year. And at the moment, what we're doing is we're in the validation stage of the coupled system. So we're working very closely with our partners in particularly Malawi, with the Ministry of Health there. We also have partners in Ghana, where we're really trying to focus on the validation of the system for, should we say, hindcasts, so forecasts that have been made over the last 10 years, for which the health data is available. And my colleague Rachel was working with me at ICTP before she moved to Spain on this aspect. We're continuing to collaborate on this aspect. So what we're hoping is that in the next, should we say, 6 months, the system will be fully validated for our target partner countries. We also have a good relationship with the Ministry of Health in Uganda that have provided us with a very good data set. And then in the next year, we want to actually put this into essentially a decision support system that will be provided to the Ministry of Health in Malawi on a kind of, should we say, prototype. It's very important that these systems are validated. What we don't want to do is give out bad information. We want to try and portray the information with the, should we say, an assessment of the potential errors, the potential uncertainties. And so what I need to emphasize is that we're working very closely with our colleagues at these institutes. The colleagues in the University of Blantyre, for example, we've had 8 people, I think, over the last 3 or 4 years spending many months, normally coming over for 4 to 6 months at a time, working very closely with us so they can see how the system's developing, what we're using, and particularly for the dissemination. One slide I didn't show, actually, right at the end of the talk, actually, is that we really want to see how we can potentially actually disseminate this forecast information. So we also have colleagues there up on the top of this antenna that have been setting up long-range wireless links to actually try and get this information to local clinics and also take real-time health information from those clinics. So what I want to emphasize, although I've only talked about the modeling aspect of the project, it's a fully integrated project that's going right from the weather information right through to the end users, where we're really working with our end users and our colleagues at both in the Ministry of Health and also at the universities to really try and have a system which is going to be used sensibly and is going to be, should we say, fully understood. And I think some of the work as well that Rachel will be showing in her posters really emphasizes that aspect of the forecasting system. I've tried to just focus on one core aspect in the presentation today. Thank you for the question.
Thank you very much. I'm afraid we have to end here to prepare for the next press conference, which will be on flood disasters. But you are welcome to approach our speakers at this time. And you can also book rooms for interviews afterwards if you so wish. Thank you very much. And thank you to our speakers. Very good. Thank you.